Hello, and welcome to our astronomy course. Today, we have lecture number 18. The topic of this lecture is uh, active galaxies and supermassive black holes. So we continue study previous topic. What I may say for the beginning, you know, supermassive black holes lies of solar masses at the center of the most galaxies. Such monster can release tremendous energy and containing millions of to because eruptions that were the largest supernova. Imagine that word I'm recently said you. Yet most galaxies that contain supermassive black holes are not erupting. You may ask why. The study of supermassive black holes will introduce you to some of the most extreme conditions in the universe. Let's start with the first subtopic of today's lecture, active galaxy nuclei. With the construction of the first large radio telescope, it's not far, yet according to the astronomical times. It's in 1950, astronomers discovered that some galaxies, dubbed radio galaxies, were bright at radio wavelength. Later, when telescopes went into the orbit, these galaxies were found to be emitting energy at other wavelengths as well, and they became known as active galaxies. Modern observations show that the energy comes from the nuclei of the galaxy, which are now known as active galactic nuclei, AGN. Only a few percent of galaxies are active. So, your first step is to meet these particular galaxies. In 1943, Mount Wilson astronomer Carl Safer published his study of spiral galaxies. Observing at visual wavelength, Safer found that some spiral galaxies have small, highly luminous nuclei with specular spectra. Let's look at this lightly. These galaxies are known as Safer galaxies. The spectrum of a normal galaxy is the combined spectra of many billions of stars. So, galaxy spectra contain only a few of the strongest absorptive lines found in stellar spectra, right? Okay, but the spectra of Safer galaxy nuclei contain broad emission lines of highly ionized atoms. Emission lines suggest a hot, low-density gas, and the presence of ionized atoms suggests that the gas is very exciting. The width of the spectral line suggests that large Doppler shifts produced by high velocity in the nucleus. Gas approaching Earth produces blue shifted spectral lines. I hope you remember Doppler effect. Red and blue shift. Okay? So gas going away produces red shift light. The combined light, therefore, contains broad spectral lines showing that the velocities at the center of Kuiper galaxies are roughly 10,000 kilometers per second, about 30 times greater than velocities of the center of the normal galaxies. Sometimes violence is happening in the scores of Kuiper galaxies. Now, about 2% of spiral galaxies appear to be Kuiper galaxies, and they are classified into two categories. Type 1 Kuiper galaxies are very luminous at X-ray and ultraviolet wavelengths and have the typical broad emission line with sharp, narrow core. Rapidly moving thus produces a broad part of the line, but some lower velocity gas must also be present to produce the narrow core. Type 2 Kuiper galaxies have much weaker X-ray emission and have emission lines that are narrower than those of type 1 Kuiper galaxies, but still broader than spectral lines produced by a normal galaxy. The brilliant nuclei of Kuiper galaxies fluctuate rapidly, especially at X-ray wavelength. A Kuiper nucleus can change its X-ray brightness by a significant amount in only minutes. As you saw, when you studied neutron stars, an astronomical body cannot change its brightness in a time shorter than the time it takes light to cross its diameter. If the Kuiper nucleus can change in a few minutes, then it cannot be more than a few light minutes in diameter. In spite of their small size, the cores of Kuiper galaxies produce tremendous amounts of energy. The brightest emit 100 times more energy than the entire Milky Way galaxy. All of this is consistent with a supermassive black hole lurking in the center of these galaxies, orbited by hot accretion disks no bigger than Earth's orbit. Imagine galaxy sizes and only tiny Earth's orbit. The shapes of Kuiper galaxies provide an important clue. Some astronomers argue that Kuiper galaxies are more common in interacting pairs of galaxies than in isolated galaxies. Also, about 25% have peculiar shapes suggesting tidal interactions with other galaxies, as you may see in this slide. This statistical evidence hints that Kuiper galaxies may have been triggered into activity by collisions or interactions with companions. You will find more such evidence as you study other kinds of active galaxies. Beginning in 1950, radio astronomers found that some sources of radio energy in the sky consisted of pairs of radio bright regions. When optical telescopes studied the locations of these double-lobed radio galaxies, they revealed galaxies located between the two regions emitting radio energy. Unlike Kuiper galaxies, where the energy comes from their core, these radio galaxies were producing energy from two radio lobes. Study cosmic jets and radio lobes and notice 4 important points and 2 new terms. First, the shapes of radio lobes suggest that they are inflated by jets of excited gas emerging from the nucleus of the central galaxy. This has been called the double exhaust model. And the presence of hot spots and synchrotron radiation shows that the jets are very, very powerful. Active galaxies that have jets and radio loops are often deformed or even interacting with other galaxies. The complex shapes of some jets and radio loops can be explained by the motion of the active galactic nuclei. A good example of this is 3C31, the 31st source in the third Cambridge catalog of radio sources. So why we have this numeration? With its twisting radio loops. These jets are consistent with matter falling into a central supermassive black hole. You have seen similar jets produced by accretion disks around protostars, neutron stars, and stellar mass black holes. Also, the details are not understood. The same processes seem to be producing all of these jets. The evidence shows that the cores of most galaxies are occupied by supermassive black holes, and that matter flowing into the black hole can produce tremendous energy and eject jets in opposite directions. In fact, the violence of these active galaxies is so great, and it can influence entire clusters of galaxies. The Perseus galaxy cluster contains thousands of galaxies and is one of the largest objects in the universe. One of its galaxies, like NGC 1275, as you can see in this slide, is one of the largest galaxies known. It is pumping out jets of high-energy particles, heating the gas in the galaxy cluster, and inflating low-density bubbles that distort the huge gas cloud. The hot gas absorbed in galaxy clusters is heated to multi-million degree temperatures as galaxy after redshifting the hydrogen Balmer lines to see if they could be made to agree with the lines in 3C 273, 3C 273 factor. At a redshift of 15.8%, these lines clicked into place, as you may see in this figure. Other quasar spectra quickly yielded to this approach, revealing even larger redshifts. Numerically, the redshift zeta is the change in wavelength delta lambda divided by the unshifted wavelength lambda naught. So redshift delta lambda divided by lambda naught. According to the Hubble law, these large redshifts imply very large distances. The first quasars studied were the brightest ones, but surveys have found lots. The Sloan Digital Sky Survey found 90,000. Most of these quasars have very high redshift and lie very far from Earth. Many quasar redshifts are greater than 1, and that may strike you as impossible. The Doppler formula implies that such objects must have velocity greater than the speed of light. But according to the classical science, it's impossible. Speed of light is the maximum speed in our universe. Another universe we do not know for today. But the Doppler formula you have studied apply only to low velocity. At high velocity, relativistic effects come into play. So quasar redshift greater than 1 are indeed possible for the very distant quasar. You understand me? That's very, very interesting part. Also, the quasars are far away. They are not very faint. A galaxy at such a distance would be faint and extremely difficult to detect. But quasars shown up on photographs as little points of light. If you put the apparent brightness and huge distances of quasars into the magnitude-distance relation, you will discover that quasars must have 10 to 1,000 times the luminosity of a large galaxy. So quasars must be ultraluminous. Soon after quasars were discovered, astronomers detected fluctuations in brightness over times as short as a few hours. Because an object cannot change its brightness appreciably in less time than it takes light to cross its diameter. The rapid fluctuations in quasars show that they are small objects, not more than a few light hours in diameter. By the late 1960s, astronomers faced a problem. How could quasars be ultraluminous, but also very small? What could make 10 to 1,000 times more energy than a galaxy in a region as small as our solar system? New large telescopes in space and Earth's surface have revealed that quasars are often surrounded by hazy features whose spectra resemble those of normal galaxies. In addition, radio telescopes have revealed that some quasars are ejecting jets and inflating radio loops. The evidence is now overwhelming that quasars are the active cores of very distant galaxies. And many of those galaxies are distorted or interacting with other galaxies. Quasars have tuned out to be the most extreme of active galactic nukes. Let's start another subtopic of today's lecture, supermassive black holes. You know, in the previous two modules, you learned that most galaxies contain supermassive black holes at their center. How do objects produce eruptions, and how did they form? Matter flowing inward in a galaxy must conserve angular momentum and spin faster, forming a flattened disk around the central black hole. Even a supermassive black hole is quite small. A 10 million solar mass black hole would be only 1/5 the diameter of Earth's orbit. Imagine Earth's orbit, 1/5. And that means matter in a accretion disk can get very close to the black hole, orbit very fast, and grow very hot. Theoretical calculations predict that the central cavity in the disk around the black hole is very small, but that the disk there is puffed up and thick. This means the black hole may be hidden deep inside this central well. The outer part of the disk, according to the calculation, is a fat, cool torus, donut shape, or dusty gate. Astronomers can see the black hole, but in some active galaxies, the Hubble Space Telescope can detect the outer parts of the central disk, like in this slide. spectra reveal the speed of rotation, and Kepler's third law yields the mass of the central object. Most supermassive black holes have masses of a few million solar masses, but the most massive found contains 18 billion solar masses. As the matter in the teeth drifts inward, it must orbit faster, and friction heats it to high temperature. The outer disk may be cool, thick, and dusty, but the innermost disk is very thin and very hot. Near the black hole, the gas can have temperatures of millions of degrees and emit X-rays before it falls toward the event horizon and vanishes. No one knows exactly how the supermassive black hole and its disk produce jets of gas and radiation. But magnetic fields are a factor, because the disk is at least partially ionized. Magnetic fields are trapped into the gas of the disk and drawn inward and wound up. Theory suggests that this creates powerful magnetic tubes extending along the axis of rotation, channeling hot gas outward in opposite directions. The jet seems to originate very close to the supermassive black hole and are then focused and confined by the enclosing magnetic tube. The mechanism that produces jet is understood in only a general way, but astronomers are now trying to work out the details in general way. But this is very nice job for your future. Okay? How do supermassive black holes produce all of the different kinds of active galaxies that are observed? When a field of research is young, scientists find many seemingly different phenomena, such as paper galaxies, double-lobed radio galaxies, quasars, cosmic jets, and so on. As the research nature, the scientists begin seeing similarities and eventually are able to unify the different phenomena as different aspects of a single process. This organization of evidence and theory into logical arguments that explain how nature works is the real goal of science. Astronomers studying active galaxies are now developing a unified model of active galaxies core. Amongst the black hole is the centerpiece. According to the unified model, what you see when you view the core of an active galaxy depends on how this accretion disk is tipped with respect to your line of sight. You should know that the accretion disk may be tipped at a steep angle to the plane of its galaxy. So just because you see a galaxy face on doesn't mean you are looking at the accretion disk face on. Are you agree with me? And if you view the accretion disk from the edge, you cannot see the central area at all, because the thick, dusty torus blocks your view. And instead, you see the radiation emitted by gas lying above and below the central disk. Because this gas is farther from the center, and it is cooler, orbits more slowly, and has smaller Doppler shift, and thus narrower spectral line. And this might account for the type 2 Seyfert galaxy. If the accretion disk is tipped slightly, you may be able to see more of the intensely hot gas in the central cavity. This broad line region emits broad spectral lines because the hot gas is orbiting at high velocity and the high Doppler shift mirror out the line. Type 1 Seyfert galaxies may be explained by this phenomenon. But I want to ask you, what happens if you look directly into the central cavity? According to the unified model, you would be looking directly into the high energy jet, down the dragon's throat. A few such objects have been found. They have a featureless spectrum and fluctuate in brightness in only hours. The unified model is far from complete. The actual structure of accretion disk is fully understood, not only for you, for scientists too, as is the process by which the disks produce chaff. Unification does not explain all of the difference among active galaxies. Rather, it is a model that provides some clues to what is happening in the core of active galaxies. Most galaxies contain a supermassive black hole at their center, but only a few percent of galaxies have active galactic nuclei. And that must mean that most of the supermassive black holes are dormant. They are sleeping. Presumably, they are not being fed large amounts of matter. A slow trickle of matter flowing into the supermassive black hole at the center of our galaxy could explain the mild activity seen there. But it would take a larger meal to trigger an eruption such as those seen in active galactic nuclei. What could trigger a supermassive black hole to erupt? The answer is something that you studied back in time. You have also seen in the previous module how tides these interacting galaxies and rip matter away into tidal tails. But mathematical models show that those same interactions can throw matter inward. A sudden flood of matter flowing into the accretion disk around a supermassive black hole would trigger it into eruption. And this explains why active galaxies are often distorted. They have been twisted by tidal forces as they interacted or merged with another galaxy. A quasar has been found at the center of an elliptical galaxy that is surrounded by shells of stars. In the previous module, you learned that such shells are evidence of a recent encounter with another galaxy. Some active galaxies have nearby companions, and you can suspect that the companions are guilty of tidally distorting of the other galaxy and triggering an eruption. Tidal forces between galaxies span distances of 100,000 light years or more. But the same bit of physics becomes important when matter comes very close to a supermassive black hole. Let's look at this figure, please. This figure shows how a passing star would be ripped apart and at least partially consumed by the black hole. Inflowing gas, dust, and occasional star would be an energy feast for a supermassive black hole. A few dozen supermassive black holes have measured masses, and their masses are correlated with the masses of the close galaxies, nuclear bulges. In each case, the masses of the black hole is about 0.5% of the mass of the surrounding nuclear bulge. But there is no relationship between the masses of the black holes and the masses of the disks of galaxies. This bit of statistics provides an exciting insight into how galaxies form. Apparently, a galaxy forms its nuclear bulge first and it dies later. As the nuclear bulge forms, a small fraction of the mass, lacking orbital moment, sinks to the middle where it forms a supermassive black hole. All of that matter flowing together to form the black hole and would release a tremendous amount of energy and trigger a violent eruption. Long ago, when galaxies were actively forming, the birth of the nuclear bulges must have triggered active galaxies' nucleus. The formation of a nuclear bulge was evidently a violent process. Recall from previous lecture that the disk of the Milky Way galaxy formed late as the matter settled into the galaxy. But that stage, the nuclear bulge and central black hole were formed, and the gradual development of the disk didn't trigger a violent eruption. So disk formation is wimpy, said one astronomer. If supermassive black holes form with the nuclear bulges, then the black holes have been in galaxies since the beginning, and it should be possible to trace their history. When you look at a photo of galaxies with large redshifts, the look back time is large, and you see the universe as it was long ago. The light journeying from such a great distance carries information about how the galaxies form and develop. In the next model, you will see evidence that the universe began 13.7 billion years ago, and that it has been expanding over since. The first clouds of gas began forming stars and falling together to form great star clouds that became the nuclear bulges of galaxies, and the supermassive black holes form at the same time. Matter flooding into these black holes should have triggered powerful outbursts. Some of the most distant quasars could be caused by the formation of supermassive black holes. But these extremely distant objects are difficult to image with existing telescopes. Most of the active galaxies that astronomers see with today's telescope have been triggered into eruption by the interaction and collision of galaxies, a process that throws matter into the central black hole. You should also know that galaxies were closer together when the universe was young and had not expanded very much. Because they were closer together, the forming galaxies collided more often. And also, as small galaxies fell in war and formed halos around the nuclear bulge, matter could have been fed in war to the supermassive black hole and triggered more eruptions. Quasars are most common with redshifts of a little over 2 and less common with redshift about 2.7. The largest quasar redshifts are over 6, and such high redshift quasars are quite rare. Evidently, astronomers see few quasars at high redshift because they are looking back to an age when the universe was so young and it had not yet formed many galaxies. At redshifts between about 2 and 2.7, galaxies were actively growing, colliding, and merging, as you may see in this slide. And quasars were about thousands times more common than they are now. But nevertheless, even during the age of quasar eruptions must have been unusual. At any one time, only a small fraction of galaxies had quasars erupting in their core. As expansion carried the galaxies apart, and as galaxy formation became less active, quasars became less common. Then where are all the dead quasars? How do you think? An astronomer commented recently, there is no way to get rid of supermassive black holes. So all of the galaxies that have short-lived quasars must still have those supermassive black holes. But where are all those dead quasars today? You know where to look. The core of galaxies. Most galaxies contain supermassive black holes at their center, but they have gobbled up most of the nearby gas, dust, and stars, and they are dormant. Now, our own Milky Way galaxy could have had a quasar at its core long ago, but now its central black hole is on a strict diet. Occasional interactions between galaxies can throw matter inward and nudge a sleeping supermassive black hole into eruption to become a safer galaxy or a double-lobed radio galaxy. Active galaxies are not some rare kind of galaxy. They are normal galaxies passing through a stage that many galaxies experience. They are not really peculiar. They are an important part of the story of the formation and evolution of galaxies. Let's look at one scientific argument. Why are most quasars so far away? You know, sometimes a scientific argument hinges on simple geometry. But in this case, you need to add a second factor. First, quasars are the active cores of galaxies, and only a small percentage of galaxies contain active core. To sample a large number of galaxies in your search, you must extend your search to great distances. Most galaxies lie far away because the amount of space searched increases rapidly with distance. Just as ball seats in the baseball stadium, imagine, are far from the home plate, and most galaxies are far from our Milky Way galaxy. That all stars you see on your head. Consequently, most of the galaxies that might contain quasars lie at a great distance. But a second factor is much more important. The farther you look into space, the farther back in time you look. It seems that there was a time in the distant past when quasars were more common, and consequently you see most of those quasars at large look-back time, meaning at large distances. For these two reasons, most quasars lie at great distance. Now, expand your argument. What observational evidence makes you think that quasars must be triggered into eruption? Let's make some symmetry. First, called radio galaxies, active galaxies are now known to emit energy at many wavelengths. Because the energy comes from their core, they are known as the active galactic nuclei, AGN. Taper galaxies are spiral with small, highly luminous cores and spectra that show the nuclei contain highly excited gas. Double-lobed radio galaxies emit radio energy from areas on either side of the galaxy. As described by the double-exhausted model, these lobes appear to be inflated by jets ejected from the nucleus of the galaxy, where the jets push into surrounding gas and they form. Jets from active galaxies are at least in part responsible for heating the gas trapped in clusters of galaxies. The quasars have a star-like appearance, but very large redshifts that imply they are very distant. To be visible at such distances, quasars must be ultraluminous, yet rapid fluctuations in brightness show that quasars must be small. The best images show that quasars are embedded in fuzzy galaxies that are often distorted or have close companions. From this, astronomers conclude that quasars are highly luminous cores of very distant active galaxies. Matter flowing into a supermassive black hole must conserve angular momentum and form an accretion disk that is thick and dusty at great distance, but thin and hot closer to the black hole. A few such disks have been imaged in the cores of active galaxies, and their rotation permits the measurement of the mass of the black hole. The spinning disk pulls in and winds up the magnetic field, and by a process not yet understood, by the way, this magnetic field ejects and focuses two jets of radiation and high-speed gas in opposite directions along the axis of rotation. Okay? Supermassive black holes erupt only when large amounts of matter flow inward, so most galaxies have dormant cores. During interaction and collision, tides can throw matter inward and trigger eruption. And this explains why active galaxies are often distorted or have nearby companions. Because quasars lie at great distances, and astronomers see them as they were long ago, over 10 billion years ago, when the universe was young and just forming galaxies. According to the unified model, what you see depends on the tilt of the accretion disk. If you see into the core, you see broad spectral lines. If you see the disk edge on, you see only narrow spectral lines. And if the jet from the black hole points directly at you, you see a featureless speck. Because the mass of a supermassive black hole is related to the mass of the nuclear bulge around it. And astronomers conclude that the black hole formed soon after the beginning of the universe, when the first gas cloud fell together to form the nuclear bulge. Mergers with smaller galaxies are thought to have built the colors of galaxies and may have triggered eruption of the core. But gas falling into form, the disk was not violent and didn't trigger eruption. Some of the most distant quasars may be erupting because of the formation of supermassive black holes. But most activity is triggered by interaction and collisions with other galaxies. Collisions were more common in the past, before the universe had expanded very fast. This acceleration, I hope you remember. The age of quasars at redshifts from about 2 to 2.7 was a time when galaxies were actively growing and merging. The supermassive black holes that produce quasar eruptions are now mostly dormant because very little mass is flowing into them. You know, galaxy can be triggered to become an active galaxy is if tied through matter inward during an interaction with another galaxy. I think it's enough for today. Any questions or propositions? You may ask him even in internet too. I hope you enjoyed this lecture, and I'm looking forward to see you next time. Bye.